The logic part of the ALU could be constructed using a multiplexer plus some gates. And we are going to implement 4 basic logic operations: AND, OR, XOR, and NOT. So basically here we have a 4 to 1 line multiplexer which has 2 select inputs, S0 and S1. It has 4 inputs. The inputs that we have for the multiplexer are AI and BI, AI or BI, AI XOR BI, and NOT AI. And the output will be one of those depending on the values that we have for the select lines. So here you can see the function table for the logic part, the logic circuit that we are going to use for the ALU. With S1, S0, we will have AND when S1 and S0 are 0 and 0. We will have OR when they are 0, 1. We will have XOR when they are 1, 0. And we will have NOT A as the output when we have S1 and S0 equal to 1 and 1. Then we can combine the arithmetic unit and the logic unit with each other using a 2 to 1 line multiplexer, which will obviously have one select line, in order to have the arithmetic logic unit. Okay, so the whole thing will be together. Here you can see the schematic for one layer of the arithmetic logic unit, which stands for a single bit operation. For n bit operations, we would need to have n number of these, let's say, schematics on top of each other. For the arithmetic unit, we have AI and BI as the data inputs, S0 and S1 as the selector inputs, and for the logic units we have AI and BI similarly as the data input, and S0 and S1 as the selection inputs. However, for the arithmetic unit we would need to use some carry in and we will have some carry out. The carry out of each level will be used as the carry in for the next level, but as the carry in of the first level, or C0, we will get it through some selection input which is called as C in. So therefore over here we will have AI and BI as the data inputs, and then C in, S0, S1 and S2 as the selection inputs. And over here you can see how the whole arithmetic logic unit will look like, referring to the select inputs S2, S1, S0 and C in, and then we can see which operation is going to be performed. The last 4 operations are the logic operations. Let me maybe change the color and the size. So the last 4 that you see here, these are the logic operations, and the upper ones are the arithmetic operations. You should also see here that for the logic operations we have S2 equal to 1. So if you go back over here, S2 is here. When S2 is equal to 1, it means that we will take the second input to the multiplexer and it will appear at the output of the multiplexer. So you can see that the logic operations will be considered. One important thing here to notice is that when S2 is equal to 1, when we have this situation, then the value that we have for S1 over here will not be important because it is not used with our logic circuit. Yeah? It is only used for the arithmetic part. And you should also see it here. So S2 equal to 1 means that S1 is not important. And then depending on the values that we have for S0 and C in, where we will have 4 possible options, one of the 4 logic operations will be performed. On the other hand, when S2 is equal to 0, we are going to have arithmetic operations. It should also be clear here. When S2 is equal to 0 here, then the arithmetic circuit will be selected as the input to the multiplexer and it will be passed to the output. Therefore, we will have indeed the arithmetic operation, and the value for all the other 3 select inputs will be important. We will have 8 possible operations. You can see them here: transferring A, incrementing A, addition, and so on and so forth. So basically, with this configuration, we will have the arithmetic logic unit implemented.